In sketching the electric field between Q1 and Q2, recall that we took the circle around charge Q1, and at each point we drew the electric field E1 that results from the charge Q1. We went all the way around the circle. At a point here, which we'll call point A, recall that E1 was in this direction. We had an E2, an attraction toward the charge Q2 of a hypothetical positive test charge, and we got the resulting vector here that deflected the E1 vector slightly down this way and made it a little bit longer. At the point C, the two vectors would have been in the same direction, so that the resultant would be greater than either of the two vectors. At point B up here, the effect of Q2 would have been pretty small. We would have just deflected this vector slightly in the direction of Q2. And as we move further and further back away from Q2, it has less and less effect, so that the electrostatic field pretty much becomes radial as we get out here. It's very close just to the field that we would have from Q1. Now as we get down here again, it starts being deflected back toward Q2. The field of Q2, the influence of Q2 starts to be felt more and more strongly as we move around to this point. Now, let's think about what would happen if we started, let's say at this point, and everywhere moved perpendicular to the electric field. Now think about this. If we're moving a test charge perpendicular to the electric field, the force on the test charge, of course, is parallel to in the direction of the electric field. So if we're moving perpendicular to the electric field, we're moving perpendicular to the force that the electric field exerts on that charge. That means that we're not doing any work against the field, and the field's not doing any work on us. That means, recalling the definition of potential or voltage as work per unit charge, number of joules per coulomb, that tells us that the electrostatic potential of the charge is not going to change if we move it perpendicular to the field lines. We move for free. There's no increase or decrease in the potential energy of a charge. There's no increase or decrease in the electrostatic potential along a curve that moves always perpendicular to the field lines. Now, if we move perpendicular to the field lines out here, we're going to pretty much just stay with the circle, because the field is pretty much just radial, straight away from the charge. This vector is not very well drawn. It should have been in this direction. I just noticed it was drawn kind of carelessly, apparently. In any case, every vector out here is going to be pretty much perpendicular to the circle. It's not going to vary much because Q2 is not going to have a whole lot of influence out here, although it will vary some. Let's worry about the variation when we get in here where we can see it. Now, as we get in closer and closer to the point B, the influence of the field E2 or the influence of the charge Q2 starts pulling the field lines down this way. So instead of being radial, the field lines, not sure how to hold that pin so you can see it, instead of being radial, the direction of the field lines tilts down this way a little bit, which means that the perpendicular to the radial is going to do what? Well, let's see if I can hold these things perpendicular. If these are perpendicular and the radial line is deflected like this, the perpendicular is going to be deflected accordingly, so that the perpendicular, instead of staying with the circle, comes out like this. That means we're going to start cutting inside the circle, and the circle's actually going to end up flattening out as we come down here and try to keep remaining perpendicular to the field lines. So we see that equal potential lines are always perpendicular to the field. Now we could draw the equal potential lines around the charge Q2 also. This picture isn't in your notes because I thought it might be misleading without an explanation. The question is, what does the equal potential look like in the vicinity of Q2? Now charge Q2 we're going to have more flattening as we come around here. The question I want to raise is it possible for the thing actually to indent a little bit like this? Okay, this one flattens out. Can this one indent a little bit? It's conceivable, because the electric field pushing away here is going to strongly influence the electric field pulling in toward Q2. So the actual answer to that question is mathematical, and more mathematical than we want to get, because the shapes of these things are fairly complicated. You have to use some pretty good mathematics to get the shapes of these surfaces. But we see here also the vectors around the circle that we drew about Q2. At this point, there's a fairly strong repulsion from Q1 and a pretty good attraction toward Q2. The repulsion from Q1 might still be even greater than the attraction toward Q2, which will give us a vector in this direction. Out here, the effect of Q1 is diminishing. Q2 is still quite strong, so we end up with something like this. Out here, Q1 will have a little bit of an effect against this blue vector here, shortening it slightly, and similarly down here. And you might think about what that does if this shape is accurate. Of course, it's not totally accurate, but look at the basic characteristics of this thing. Does it flatten out here? Does it indent here? Is that a good shape for this thing? Or should it be something else? In playing around with the fields program, you'll be able, of course, to investigate these sorts of things. And we'll talk about that program in a minute.